My name is Ray Bell. I'm the CEO of Aetheros, and I'd like to start by putting out a thank you to Hubbell, Aclara Hubbell, and Ericsson for their participation with us in this use case, AMI 2.0. With that, we have Kevin Lindman over there and Tom Wilson. Thank you, guys. When we were asked to participate in this use case, we looked at the description, and it really asked us to look at what is AMI 2.0, and then more importantly, what are the applications that 2.0 can bring to enable operational efficiencies in the network. So we wanted to keep it simple. We're working on real world data. We currently have over 1.5 million CAD-M AMI 2.0 meters in the field outside the US, but we're using those data sets behind our analytics and our analysis for today's presentation. If you boil down AMI 1.0, it was, we started this in 2003. We needed to move from a digital meter to a mechanical meter to a digital meter. We needed to get interval data to market every day by midnight, get the data to the back office by midnight and into the market by 6 a.m. And so that was kind of the use case that drove the technology approach. I was part of the team in the early days at Silver Spring when we started looking at building mesh technology, and cellular really wasn't an option for us at that point in time given the cost models in the United States. So it was pretty simple. How do we get revenue meter read data to market? How do we do actuator control, service switch control? How do we look at some power quality information from the socket, from the service point? And how do we provide realistic event reporting for outage events, quality of supply events, device events? You fast forward 20 years later, and we have a lot bigger challenge to address, right? We have the electrification of the vehicle and the impact on the grid. We have renewables and their proliferation throughout the homes, so micro-generation, storage. How do we integrate all of this new use cases into AMI? And what we looked at that, and we said, well, it really, at the end of the day, if you boil this down, I need an open, standards-based edge computer in the meter. We need to enable utilities and application developers to develop applications just like they develop them on your mobile phone today. There should be no barriers. We should not present, closed barriers to those developers. So how do we empower them to write applications that can solve problems? We'll talk about what some of those applications are in a minute. But that was the biggest thing. How do we provide the ability to have autonomous control at the edge to protect the transformers from overload, like my previous colleagues spoke about in their use case? How do we provide semi-autonomous control where we have logic operating in the device and it's getting market signals, and how does that influence the edge capability or the edge action? And then people use software-defined grids. They use digital twins. It's a term. How do we create a digital representation of the actual distribution and generation network? And so people are like, well, what's a digital twin, right? A digital twin is an up-to-date representation of an element in the network. That element could be the meter itself. It could be the transformer above that meter. It could be the circuit, substation feeding that transformer. It could be the grid itself. And so what AMI is really about is how do we actually support the creation of digital twins so that we can then use that information to improve the efficiency of the grid. The other interesting point that we've been working with is waveform data. So the interesting thing about an AMI 1.0 meter, yeah, it was great. It was a 4-quadrant digital meter. It had a calendar, it had a clock. You know, we're recording at, started at 30-minute intervals. Now we're, down to 5-minute intervals, with 60 channels of data with a DLMS meter, or 20 channels of data with an ANSI meter. That's a lot of data. But today's meter can actually bring that sampling down to a lot more granular. And in today, the meters we're working with can actually sample at 16,000 times a second. And at 16,000 times a second, it's kind of like thinking about a movie, a movie at 280p or 8K. They're both a movie. One's kind of grainy, but one's very crisp and clear. And so if you're looking to build a digital twin into your network to actually analyze what you can do with that, how you can reduce your line losses, how you can target foliage management, how you can extend the life of that equipment from it being overloaded, this information will allow you to analyze that and actually save tens or hundreds of millions of dollars over the life of the meter. What are the use cases? There's a lot. This slide, what we wanted to do is kind of, break this down for you into two kind of categories. Visibility, applications that give you visibility into your network, and then applications that give you control over your network. And what's interesting in data analytics, and one of my colleagues, Dr. Riken, will be here tomorrow with me. He'll be going a really deep dive into what these applications are. He'll be giving some demonstrations of them, so I won't go into them too much today. He'll be up here tomorrow. Please come and listen. He's going to, it's very enlightening. But we've been learning a lot about this from Dave and team. But basically, what comes out of this is you don't need every meter to report data every second. That's the bottom line, While a model can get, with more frequency updates, you can actually get towards that 4-second, 1-second model. But if you look at the use cases, they're very few. So you're not going to put that kind of reporting model on every revenue meter in your network. It would be insane, right? So you may put that reporting model on various meters out in your circuits to protect things, where you can see a line break, or you can see the type of use case to the right. To the left, what we found is that almost all of the applications do very well at 2-hour reporting. And this is a really important takeaway, because our position and what we've seen with real-world data is that you can build a very dense network, thousands of meters on a sector, that can actually report every 2 hours. And the next slide's kind of a very interesting slide. This is actually modeled from the data being taken from the meter. It's not just estimated. This is actual data. And if you look at AMI 1.0, if we're doing 5-minute intervals, 20 channels, something like that, well, I think it is, we're getting about, 60 kilobytes a day. So AMI 1.0, all the data you want for intervals, events, outages, about 60 kilobytes a day. If you're sampling at 16,000 times a second, and you're getting phasor data on current and voltage data, That data from what the software we have running on the AMI 2.0 meters with Hubbell, or Aclara Hubbell, will actually generate 28.8 megabytes a day. A day, not a month, but a day. And that information can actually give you a crystal clear view of the day-to-day operations of your network through bringing that back, running advanced machine learning, AI, creating a digital twin into your infrastructure. You can direct your operational crews. You can improve your operation. You can improve the maintenance of your network. You can improve the asset life of your devices. And this will actually help you pay. You know, if you put that into your rate case, you're saving hundreds of millions of dollars, right, which will quickly pay for that private LTE network in your utility, right? As you go to justify that in your rate base, you know, it's not just about revenue metering, it's about actually preparing yourself to have a highly efficient infrastructure over the next 20 years. Just a little picture. I mean, what's kind of interesting is EVs. You know, EVs, I kind of call them the dumb EVs, you know, they plug in. You can tell them to turn down a little bit, you know, up and down, go high charge, low charge, medium charge. But the emerging EVs actually now have a revenue meter inside them. We actually have one over at the Hubbell booth you can go take a look at. And what does this let you do? This actually lets you build a EV-specific rate plan, right? So you can actually control that EV as a separate element. It takes roughly the same load as the house. So even though that meter is a sub-meter behind the house, you can actually now have, you know, and in California they're driving this with their EV strategy. You can actually now go and put a metered EV into the house. Now, we can still support the dumb EV SCs. We can talk to them over Wi-Fi. We can talk to the car. We can talk to the chargers. And we can have them scale back. But we think the smart EV is kind of going to start to take more and more traction. Lots of line equipment in Hubbell, as you know. It's not just about meters. We have, you know, we have all the line equipment, and so we see that as very much part of the AMI 2.0 network. We see that equipment and the meters all communicating together over LTE. You know, if you think about your phones in your pocket, you can call anyone in the United States or the world and have a communication going, and that communication, those packets are moving in milliseconds. Every device on an LTE network can communicate peer-to-peer over IP, over that radio access network, without needing to go back anywhere to any data center or head end. So, I mean, look at how we communicate today with cellular. That's what we think a big value of PLTE brings to the utility. And so in our use case, what we wanted to do is show how we could use an edge application running on the meters to allow the meters to communicate to each other dynamically. When the load starts increasing, they'll start communicating more. So, you know, as their load value goes up, their need to communicate with each other goes up higher. You know, as that load decreases, they can go back to their normal state. So they don't all need to communicate at once. They need to be orchestrated in how they speak with each other. And you can do that with edge intelligence. But this will show you how the packets, the little red packets, go from meter 1 to meter 3. The other topic is in a private LTE network, you can actually optimize the configurations. It's very, you know, it's got a lot of knobs in here, and if you're a network engineer, you know what these words mean. I won't go over them here today. But you can actually optimize the uplink, downlink capacities of that network to meet your requirements. When you're running on a public network, you're using the configurations that have been optimized for high ARPU accounts, high average revenue per user accounts. So while they support machine networking well, and you know, works quite well. We have, as I said, millions of meters on public networks today. When you're actually building your own private LTE network, you can optimize that and take advantage of that. So with an optimized network, with orchestration, you can easily, every meter can report 28.8 megabytes a day. We've proven it in the lab. We're happy to show it and demonstrate to you on CAD-M. At this point, we're going to give a little use case, our demonstration of the use case. The other thing about it 2.0 is it's really about how do we integrate these electric vehicles, these new smart appliances, renewables, battery storage. We didn't have this use case in 1.0. So this is a big challenge for 2.0. We thank Ericsson very much for supporting us. We put I don't know what happened there. We lost, I lost my screen. I don't know. There we go. You got to turn off the, I'm not touching the laptop. I'm just using this. Sorry. Thank you, gentlemen. Thanks again to Ericsson for supporting us. What we did is we have in our meter lab in Sausalito, California, we put an eNode B into the lab. We connected that with a router and over a virtual private network to the Ericsson hosted core. For anyone looking to, evaluate PLTE, it's a really low cost, easy way to do it. This network came up in less than a day. The team came out, we mounted the equipment, which you'll see, connected the VPN, and we were routing traffic that day. So it's a really, if you need to look at it in your labs, I would highly recommend this. Anterix, a shout out to them, they're great, letting you use their spectrum and an evaluation basis to evaluate the network. So our architecture had an Aclara Metrum AMI meter with an LTE NIC. The AOS software, that's our product. It's a network operating system for machines. And a transformer protection edge app running in the meter. And we had the head-end software in the back. Here's our test lab, a little picture of the test lab. You get to see the team soon, but we have our router, we have our pole-mounted eNode B, and we have our meters. Now we didn't really have 4 EVs in the lab, so what we did is we took 240 volt space heaters that crank a lot of amps, and we simulated the EV charge. We have a switch in the disconnect switch, and you can see where the EV is plugged in underneath the meter and the meter itself, and then another load on coming off the meter. There's our team that put all this together, so we want to give a shout out to the team. And so in terms of the application that we demonstrated, as some of my colleagues said, the average transformer in the United States is a 25 kVA. And I don't know if you can read the text here, but the average demand for the home, I can't read it either, is about, 1.28 kV. So if you look at the average loading on that transformer, it's running at about 25-28% during the given day. And that kind of goes up and down, as people plug things in, and that's great. Now what you have is people decide to go out and buy chargers, or EVs. And if you look at this use case, if they all plugged in 4 EVs at once, you're going to overload that transformer, right? It's going to be overloaded. And the utility has no visibility into this, no control over that. You know, you just go buy an EV, you get an electrician to put in a charger. I did that, plug it in, and away you go. So in our demonstration, what you'll see, because we have a video which will actually show it to you, is we will download an application, an edge app to the meters. Those edge apps will then monitor the real demand on the meter, running on the meter, watch the instantaneous demand. And as their demands start going up, they'll start talking to each other over the IP network, over the cellular network, over IP. In this case, we're using an MQTT message bus, field area message bus. We're all about open standards, so we looked at some of the work that OpenFMB, a working group, did with Duke and all, and they modeled the IEC SIM in Google Protobuf. So it's an open modeling of the IEC SIM standard, and our Aetheros participated in that. We extended that model to include metering. So this 61968 model. So now you had substation communications with Goose protocol formats, and you had metering data on the same format. We've posted this software as open source in GitHub because it's about enabling the community to actually, you know, evaluate and write their own apps. So we're really promoting open standards and open source models. And in this case, we'll do the demo. If I can do this. Here you're seeing the test rack that we discussed. Here's the router here's our eNode B, just a single sector eNode B. Here's our little antenna. Here's AOS. It's an application. Here the team is actually choosing to download an application to a group of meters. Clicking that, you give it a name. So we'll talk more about it. If you come by the booth, we have this up and live, and the team can actually give you a much better demonstration. This video goes pretty fast. But we're downloading, the applications being downloaded to the computer, to the meters. You can see that they're downloaded here. And you can see we have the EVs plugged in, and it's reporting its load. Someone else is plugging in an EV. It's actually producing more load on the network under that transformer. And as we turn on the fourth vehicle, I believe here, you'll see that we quickly overrun that transformer. Not a good situation. However, the software is now talking to each other. Now, in the application, there's protection for life safety, protection for opt-out, protection for all the regulatory requirements that you need. And the application logic takes this into effect and tells one of the vehicles to either stop charging or lower its charge. And here you can see that happened. It didn't have to go to the back office. There was no human intervention, right? You wrote intelligent software. You put it in the edge. You let the devices communicate to each other, and now you have autonomous control. And I will tell you, if you really want to think about AMI 2.0, it's about empowering. You cannot make all these decisions in the head end. You can bring back that digital twin data. You can build machine learning and AI across that. You can actually get invaluable information on how to go out and direct your field crews, how to stage parts, how to upgrade. You know, if I have a transformer that's failing or a cracked insulator, I know the health of other devices on my network, so I'm rolling that truck. I can actually put other inventory parts in the truck, and I can optimize my field cost for operational efficiency. This is what edge computing will allow you to do. It'll allow you to protect the network at the edge. It'll allow you to get the data you need to optimize the efficiencies of your field crews, of your asset base, right? And that's the value of AMI 2.0. And you know, some people are like, well, maybe you should just put that into 10% of the meters. Well, how do you know what 10% of the meters? You know, maybe the issue's in the other 90%, right? So you really want to put this in 100% of your meters. And you know, maybe you don't believe you need 1 minute samples of of this data. You can cut that back to 12 megs or 10 megs a day. But I will tell you, if you think about an average LTE network, CAD-M network, you might have concurrently 100 connections on that base station sector, 100 concurrent connections. Now, let's say we only going to run half of those. We'll get down to 50 connections. Okay, that's not so bad, right? I have 2,000 meters on that sector. So you divide that by 50, and you'll get the number of duty cycles that you get. And so, you know, even at an uplink rate, you know, at a good uplink rate, you're at 300 kilobits per second. And it kind of, if you're kind of towards the fringe of the network, you're going to drop down to about 150 kilobytes a second. You might even go a little bit lower. But you can actually do the math, and you can actually upload. If you're uploading roughly 2.4 megabytes every 2 hours, the average uplink time is going to take you about 1.5 minutes to 2 minutes. And so if you then, over that 2-hour window with orchestration and control, you can easily report that data over the LTE network. You don't need to aggregate into a micro mesh. We do support that technology. We have cards with micro collectors on them, you know, with LTE. If you want to, you know, start to deploy this and you have a mesh network, you're afraid of breaking the mesh, you can actually deploy one of the Hubbell cards with YSUN and LTE, which will act as an access point or a border router for your existing 1.0 meters, and you can move to an LTE model. Now, again, we believe, we're network engineers, we believe that all kinds of networking technology makes sense, not any one. But we do believe that LTE and cellular LTE meets the AMI 2.0 use cases better than the AMI 1.0 technology that we built with mesh. So that's all. That's kind of the end of my presentation. Thank you very much for listening. Any questions, we'd be happy to answer. As I said, come see us at the booth. And we have live demonstration going on, and the team can actually explain more about how the software works if you're interested. Thank you.